So I guess we can get started slowly as we review as people coming in. So this is the second class of the second half of the course, which we would like to generate new knowledge based on the data. So the first thing to do is because of we're getting information from data, we need to know how data may be generated, right? Because the sampling process where you get the data is not a straightforward exercise. It's not a deterministic process, rather it's a random variable. That's why we learn probability, right? Who you talk to or who drawn to your sample is a random process. And we don't really go into the details how your sample being drawn. We just make the simplest case where each one is being drawn equally likely. In that case, that the possible value that a sample can have would be exactly the same as what underlying the distribution is, and actually that gives us a very good knowledge of what you have drawn, right? In particular, we know that if every sample is drawn randomly, then we have law of large number, saying that if you make the sample size as big as possible, that the sample mean will be exactly the population mean. And we also learned central limit theorem, which essentially said if you're able to figure out, the distribution of the sample mean, right, which will be approximately following the bell curve, right? So these are the reason that we know how to do, and then this is why the sample mean is the thing we study, right? Because do recall that for the very first class, right, we talk about if you understand a data set, right, the most representative is the mean and median, and these are number, and then the variance will be measuring how accurate it is, right? So then we also know the sample mean will be the best guess. Later we'll talk about that next, maybe on Wednesday, talk about estimation. But that would be the main goal. So very quickly, the main theorem we have is first is the simple random sample, and they give you this property there. Okay, I think there's nothing new in this context. And do remind yourself that statistics is a function of random variable. Function means the rule that you would assign a number to what you found, right? And what a sample is a random variable, right? So that means that statistic is also a random variable. It depends on what you found. Okay, so that would be very important. So do remind yourself the sample mean and sample variance are random variable. But population mean and population variance are parameter of the model. It's what happened in population. You just don't know where it is, but it's there. It's a number. There's no uncertainty. Is there something there? Because no matter what we do, it's there, the number, right? But the thing is, who you talk to, who you draw from the sample depends on some, I don't know, unknown force, right? Or the dice. Then that one is random. Okay, there's nothing random. The population variance, population mean, those things are characteristic of what should be in the population. Okay, so there's no random variable randomness for that one. But this is the randomness because depend on what sample you draw. But no matter how big your sample is, this is still a random variable, right? But its variation can be reduced to the minimum if you have drawing a lot of sample, then you will reduce, right? If possible, can keep the voice down. So that would be the idea. Okay. So we have because we want to know the population mean. Later we will show you the sample mean is the way to estimate that, because this is the first thing we want to know, right? From a big data, right? What we don't know population, the main thing is the population mean. And the sample mean is the way to go forward, right? Again, remind you this is random variable. Okay. And that's why random variable has mean, you have the variance, right? You have the distribution, it's random variable, right? So it's hard to know what it looks like in general, right? But we know that when the sample size is large, then we have a very nice property here, right? Is the mean is say the expectation same as the population one. The variance will be inversely proportional to the sample size, right? The formula is this one, right? And that implies what we have is the standard error of the mean, right? Which is standard deviation of sample mean, right? Error is actually deviation of the sample. You can replace the name, right? So will be the sigma over root n, right? So that would be the case, okay? So law of large number, as we see, is the sample size get larger and larger and larger and larger. We'll discover the truth. Okay, so that would be we have the confidence in the process, right? The more the sample we got, then that is we get the truth. And we have the assumption that when n goes big enough, then we would of course get what we want. But what happens if what the distribution looks like, right? Because it's a random variable, right? We care about how it looks like. The shape turn out to be, luckily, it's a bell shape, right? And if n is big enough, then this is a nice bell, right? Approximate, right? Because we want n is big and how big it is, right? For application, more than 30 something or 40 will be done. And we are in the case of business statistics, so this is always not a problem. Now, the next would be talking about binary data, right? So it would be the case where it's either 0 or 1, right? This particular case is not continuous, right? In that case, it's 0 or 1 is like whether you're a man or not man, right? Whether you try the product or you like it, okay? And in that case, you can calculate the mean, right? It's adding up all the ones, and 0 over the number of them is actually proportion. So we can say this, in that particular case, we can say the pi is the mu, right? And do note that because of the way it's 0 and 1, actually the variance and mean is related, right? 1 minus the mean is the variance. Okay, so that is a very special case. We can prove it, but we don't want to bother with the math, but that would be the case. And if you talk about you just draw a single element from this data set, right? How likely you draw a guy who say like the product would be just pi, right? And this Bournois distribution, right? And then if you have sample of large size, then actually called binomial, right? And this is the binomial, and the average of the binomial, right? Is the sample proportion, right? This P is the sample average. Do note that these are random variable, right? And this is the follow directly from what we have seen. So the only thing you need to know is this, the formula, right? Is no longer have sigma, but it's pi minus 1 of pi, and you will know later that allow us a lot of convenience because of mean and variance are related, okay, for binary data. That means the central limit theorem is like this one. So that would be something that we would know, okay? So lastly speaking, I want you to know the last part, which we didn't talk too much, okay? Actually, we haven't touched it, is, okay, very nicely, we know that they follow bell curve, okay? But in order to make sure that you know what's going on, then let us we say what we have right here, right? So what it is the following. So I have the population can be any number, can be look like this shape, right? The F, okay? This is X may be income, X may be people willing to spend your product, can be follow any shape like F, right? Because anything can be fine because we don't know what it looks like, okay? And what we know is suppose we take some sample here, right? Suppose sample of size 3, right, may end up in here and here, right? We can come up with a sample mean, right? Maybe somewhere is here, right? And you can take another sample mean, maybe end up in here and here, then you can here, right? You can take many sample mean of that turn out that we know if you have the sample size is big enough, not 3, maybe 300 or 400 or 500, at the end, you'll be a bell curve, right? And if the mean of this is mu, this is also mu here, right? If the variance of this is sigma square, and this will be sigma square over n, right? Where n is the size of a sample, which we denote x bar sub n, right? So one of the main problem or one of the main drawback is we don't know sigma square. Okay, probably we hint last time. It's not easy to guess what it is, right? Without actually looking at the whole data set, right? So how this knowledge would help us, right? And then, well, we do not know sigma. So I know is the variance is sigma over n, right? Normalized is bell curve, right? So what do we learn, right? So the thing actually, right, is we can solve it. Okay, we don't know sigma. So what's the purpose of central limit theorem, right? So how do we solve this? Okay, and obviously, if you don't know sigma square, right, one of the hope is we do the sample variance S square, all right, and hope that S square will be close enough to sigma square and every interpretation we have would work, right? So what we hope is, okay, is the following, right? We hope to have, right, because we hope if we take this guy, right, minus the mu over sigma over root n, right, will be a normal CO1, right, which is something we hope to have, right? Something we know, okay? But this is unknown. So what happened is, okay, can we replace this? Okay, can I, instead of that, we consider the following, right? We consider this guy. What about this one? We replace this by S. S is being the sample variance. Is it going to be same as a bell curve? Is it true it's a bell curve? Okay, so that's a problem. What does it look like? Okay, so that's the question, right? The sensitivity film tell us the pink part. What about green? Do we know anything about green? Is it going to be working or not? It's a good approximation. Okay, the question is, okay? And the answer is, if n is big enough and together with assumption that the original is a bell, then they'll be good, okay? So two conditions. One is you now have to make some assumption that the underlying looks like a bell, okay? The underlying population is a bell. We have to make extra assumption. But if we make it, this one will behave nicely. This will be almost close to bell if n is big enough, okay? But n is not big enough, that will be t. So that is how it relates, okay? So that is the idea. So let me go over the overall picture of what we're doing, right? Central limit theorem doesn't require any assumption on what's going on in the underlying population, right? You don't have to make assumption whether the underlying is bell, right? It can be anything. The sample mean will be a bell. Well, I think that's clear. The only drawback is we don't know sigma square, right? So that's why the bell actually is not meaningful, right? Because we have no idea on sigma. Of course, there may be case you know sigma square with a good estimate, that's fine, right? But in many cases, we don't know. No idea. So what we're going to do is, okay, we have to make another assumption, which most likely is okay in many applications. It's assuming underlying is following a bell. Right? Suppose I ask income data, right? If you exclude extreme rich people, usually it's a bell, right? So usually if you restrict the data in a reasonable way, then bell curve is not a big deal, right? So there's a bell. If there's a bell, then we're happy to replace this guy, the sigma of S, which estimate from data, right? Then this guy, If your n is very big, it's a bell. If n is not big, then you follow a t distribution. It's very similar to the bell curve. So that would be the idea behind. Okay, I hope that would be clear. Okay, and for application, if your n sample size, right, is like 100 or something, actually using the normal will not be, looking at bell is not a big deal. Everything would go through, no problem. Okay, which definitely apply to your case in business application. So should not be worried about that part. So we replace this, we want to know this guy, right? As I said. So the question is, we need to make assumption, extra assumption. The underlying is normal. So every x will follow a normal distribution with mean mu sigma squared. Okay. So of course, what we talked today, everything we assume is normal. It might or may not apply to your data, right? So if it doesn't apply, then you need to use other technique. Okay. For example, especially when we talk about stock price, these need not be normal. The return may be normal, but still, I mean, people figure out that it's not really normal. I mean, you need to be a little bit more careful. But it's a good approximation. Okay, it's a first approximation. I mean, there may be some difference, but in general, it's okay. Okay. So one of the good thing is, if every observation is drawn from normal, without using central limit theorem, it's normal. That is what we said in the last topic. A bell and a bell is another bell. Right? If you remember, if it's independent, right? If a bell, we combine two bell, as long as it's independent, it remains a bell. Okay? It's only true for bell, right? Just in case you forget. Okay, let me show you this slide. At the end, we actually talk about that without proving, right? It's only true for the bell curve. In case this is the case, this is the proof, right? This is not the proof, but this is the graph, right? When two bell, if they're independent, add up, it's still a bell. Okay, so that's very key. Is the bell curve. Okay, the bell, two bell, independent two bell is still a bell. Okay, and I have to emphasize that this is not true in general. Okay, only for the normal it holds. Okay, but so that's why very special. But anyway, this is, I mean, it will hold true for central limit theorem, but this, in this particular case, is hold true for any n, right? Because central limit theorem said hold for large n, right? But they say for every n, this holds true because the underlying is bell, right? So this one will be get it for 3, right? So just to make sure you see it, is just here, from here to here require central limit theorem, but here to here is free. It's free. You don't need to make any assumption. There's no big n, or this is only for n is very big. Okay. By free means any n. Any n will hold, right? So this the bell. Okay. Now we go back to the thing here. Okay. Now that is the main proof. We will not do a proof, but this is what the T will tell you is I will say a little bit, talk about a little bit intuition behind, but this guy turned out to be T distribution with degree n-1 freedom. This is proven by a student. As I told you, this is a pseudonym. For a guy who worked for a private company, he proved this theorem. Okay, and probably you ask before we go to the end, do I have the proof like this? So basically, the proof, I mean, I just mentioned 1 minute. So what the proof trying to show is they prove this minus the sample mean over this is chi-square, and they prove this is actually a chi-square n, but this is by construction, right? Or by assumption, this is normal over the chi-square root n, so that's why it's T n-1. But I'm not going to do more proof of that. In case you're interested, you can read that. But I think for undergrad, that is, we know if we replace the sigma with the S, then it will be T. The main idea is very simple. If you don't want to care about the math, the idea is very simple. The reason that it's not a bell, but a T, remember T is a shape that is normal, but more variance, right? It's fatter tail. Why is the case? The reason is the sample variance, right? In the sample, right, tend to be different from sigma, right? You get some sample, right? And that means what? The variation is different from the original, right? Then you are more likely to get more extreme values, right? Because you get fewer number, right? Then the variance can be very large, right? You get more number, you get more and more actually you will be getting original one, right? So that means that this guy has more spread out, right? So you replace that actually is like this, right? Because try to draw it out, right? Will be instead of this, actually the green one looks like this, right? More spread out, right? You get more data, likely that you can go likely to get some extreme data if you're unlucky, right? You're lucky that concentrated in some area or here or there, right, can be very large, right? Can be concentrated or separated, right? So it is possible that you get more variation, right? So that's why more spread out. Okay. And so that's why we can look at this particular example. Okay. Again, this will tell you how we are going to do the calculation. And probably at this moment, you would wonder why we care about this, okay? Because this forms a foundation we do hypothesis testing and estimation, okay? Bear with me, then we will immediately know that when we talk about this after the break. I think we can go for estimation after the break. So what do we do, right? This is the question. We know the population of mean 5, okay? And we draw a sample with a sample size 100, okay? And we know that the sample variance is 8, which calculate from data, okay? So the question is, what's probability that is less than 4.5, all right? So that's a question. And you may ask why we want to do that, okay? Let me finish that, then we will understand why, okay? So let's do the calculation, right? Because we know that the formula tells us that this guy, right, minus this is the population mean 5, okay, and over S over root n, right? This guy is actually T distribution with n minus 1, right? So S is square root of A, right? N is 100, right? So T 99, right? So what you're going to do is to rewrite everything minus this and divided by S over root n, right? And turn out this is 1.68, okay? And how can we do this calculation, okay? That we need to do it using a t-table or Excel function, right? This is less than or equal to. So that how you do it is d dot this negative 1.768, right? And 99 true. Why? Because this is less than or equal to, right? So the idea is here, right? This is 0, T99, right? 0 is here. Right? The question is this negative 1.68, okay? You want this area, right? And this area is left-hand side area. That's a distribution, F function, which is T this, right? You input this number there, 99 because n minus 1, right? So that is how you input this, right? So let me illustrate that due to the Excel spreadsheet, right? Because I hope that you know how to do that. So this negative 1.7 768, 99, true. Okay. So now we show you how to calculate this probability. So let me first tell you how you can use it. Okay. We use it. This example, the most convenient will be hypothesis testing. Okay. What hypothesis testing? What I'm doing here. Okay. Let me go back to the slide if that's okay for the Excel. So what are you doing here? This is exactly the question is, okay, from this question, what is something on population is 5, right? 5, right? And other things are actually collect from data, right? You give me 5 and you give me 4.5, right? So consider the following. You are doing audit, okay, say. And the client told you that something on average, this is 5, right? Maybe you are auditing, say, on average, say people spend $5 per table. They say, right? This is something fair, right? They say, or the machine there on average every hour you get 5 product out or every minute, right? Something like that, right? And then you collect 100 sample, you calculate how many time you spend by the machine or whatever the data tells you 4.5. Okay, the value is 8, right? What that as auditor you want to see whether the claim by the client is right? If you figure out the number is exactly 5, then you all go home, right? Fine, what he says, right? If 5.1 or 4.9 maybe okay, right? Depends on how you view, right? But if far away from 5, then you would wonder, right? Then what is far away from 5? Okay, you have to quantify the probability, right? This is exactly the case, right? This case is you claim each table generate $5, say, per hour, right? Or $500 per hour, say, for example, for a restaurant. Then you figure out that actually I look at 100 table, right? Number is 450, right? So much less than that, right? And you calculate probability that less than or equal to that number is so small, like 4%. So you have very little confidence what that guy claimed. Right? Actually, this what we cover 2 weeks later. It's called hypothesis testing. It's given that you are claiming someone claimed to you something about the population. You want to see the data support the claim or not. In this particular case, it's like so far away from the truth. That is something we want to see, right? Because look at this. Only in this case, only the mu is something that is a claim about the population, right? We just rely on that. We don't need the sigma, right? Sigma is doesn't need, right? So this is underlying why we have to learn this, because by looking at this probability, how likely is this number or less? This is very small. So it's impossible that it's come from some randomness of what we draw, right? Because you look at the data, you don't look at the whole thing. It's possible that you have unlucky draw, right? But in this case, the chance of unlucky draw is so small. It is what we call beyond reasonable doubt in the legal context, that you would think that you would, as an auditor, you don't have full confidence what that being done. Or of course, you may, as real practice, you may actually draw more sample, right? But this is what it is. Or in the case of quality control, right? The manufacturer claimed that a particular product, health product, have 5 mg of whatever ingredient you have, right? Maybe, I don't know, whatever you think, right? Then figure out that it's 4.5, you open 100 box, right? And look at this, you would say this firm is probably not telling the truth, all right? So of course, more than 5, you're happy, right? But it's way below 5, then probably it's easier, right? So that would be the idea. Why is all you stated to tell us a story, right? Because quality control, auditing, all involve looking at data to infer what's going on in the big picture. And that is the reason why we need to look at those. Does it make sense? Okay. So don't worry, we'll come to that, because this chapter is more or less form the foundation of what we're doing. We'll talk about this formally 2 weeks time, but I hope I convince you that what we're trying to do there. Okay. So here is, I do show you the t-disk, right, using Excel. But what happens if you don't have computer, right? That only all you have is the t-table, okay? The t-table you are in the textbook or whatever, it looks like this guy, okay? And this is different from the Z table because the Z table only have one table, right? That's only one table, right? Standard normal, everything can be standard normal. So you don't have to worry. But t-table, it depends on the sample size, right? Because the larger the sample, we know that is actually n go to infinity or big enough, that would become a tail, right? But if not close enough, then the tail can be very big, okay? So that means that in your t-table, indeed, we cannot show you everything, right? So for the left-hand side is the n is the sample size minus 1, right? So in our particular model, we need to look at 99, right? Because n minus 1, right? So that means that it's either 90 or 100, right? So that the first thing to do is to see we have this guy, okay? Between 99, 90 or 100, right? Because we don't have 99, right? Excel, you have 99, so no problem. But when you do your test, right, in the exam or the written exam, you don't have that, right? So how can we do that? This is the closest we can find, right? And then we try to look at the number, right? Go back to there. The number is like 1.6, 1.7, okay? And here the table doesn't give you the F, if you look at this. The table, what it gives you is this. Somewhere in the middle. Not the left, not the right. Okay, so a little bit different, okay? And you ask me why, I don't know why this is. Look at t-table, always give you this guy, okay? In the middle. So not the t-disk, but somewhere in the middle, okay? So just to make sure you know what's going on there is actually they give you this somewhere in the middle, right? The middle is 1 minus alpha, okay? And that means that this is 0 here, right? And this guy is alpha over 2, right? This is what we have. Okay. And our is, I forget what is Excel, negative 1.7, right? So it's somewhere, the question we know is purple, right? Negative 1.73, right? So we need this area. I use this horizontal line. Okay. Is that okay? Well, we need that. So look at this. Okay. Maybe usually the way you do is to be more conservative. Okay. When you do anything, usually you take 90, the smaller one. But you can take a bigger one, doesn't matter. Okay. So 1.73, okay. That is somewhere between these two numbers. Okay. So that means that if you put, say, 1.666, negative 1.666, okay, and positive 1.666, okay, the alpha will be 0.1, right? So that means that this is 90%, right? And because 90% in the middle, that means that the two sides are 5%, right? So that means that this is 5%, 0.05. Okay, here is 0.05. Okay, so that means that the probability is less than 5%. That's what we know. That's sufficient because usually 5% is the threshold that we do decision. Okay, because what is beyond reasonable doubt, which we will learn later, is 5%. Okay, so this is 5%, then we're done. So that's why this table will give you this done. Okay, is that okay? But of course, if you do assignment or if you go to work, then usually you have access to the t-table, which is the t function, right? So in the worst case, if you don't know how to do in the exam, then you can simply write the T function. You give almost full mark, right? Maybe you take out one mark for the final point, but if you write the appropriate Excel function, if this is correct, then we'll give you almost all the credit, right? In the case you don't know how to look at the table, but that would be fine. Okay, so don't worry about if you really don't know the table, we just deduct you some very little mark from that, but otherwise you should be able to tell. But okay, because this is able to tell whether you are reject or not, right? 5%. Although you don't get the exact answer, right? So this should be okay. Okay. So I guess don't worry, this thing will go over again. Okay. And this is the is already telling you what's going on here. Right? I hope that's fine. Yeah. And the proof I will basically skip. So I hope that would be fine there. So we are done with this part. Okay. So before the break, I think we're early break, but I want to review what we are doing because we've done the first chapter for the second half of the semester. Okay. So just to quickly review what we have been doing. Okay. We're doing is talking about sampling. Okay, because we want to use the data to infer what's going on, what we want to know, right? Because we don't know everything there, we just know a small part of it. Okay. And we are not looking at a particular part, right? We want this part to be representative. That means that what we drawn is actually try to drawn randomly from the set population, right? And that carry a lot of message because we do randomly. The sample mean is exactly on average will be equal to the population mean. This law of large, this unbiasedness, and when sample size large enough, that is exactly the mu, law of large number, and the shape looks like a bell curve. When n is big enough, that's called central limit theorem. And usually we can't use this directly, right? Of course, that we hope doing that right. And so that's why when we talk about application, turn out that we need to make extra assumption. The underlying is a bell curve. Okay. When the line is bell curve, then we have additional knowledge. Okay. And in that case, we can use this idea, right? It's over S over N. Okay. So probably one of the things that in your head is how and why we can assume the underlying is a bell. Okay. Why? Right? Why with bell, right? We can be anything, right? So I think this would comfort you is what we learned central limit theorem. Central limit theorem tells us that if what you observe is average value, right? That actually is a bell curve. So you can imagine IQ. Why at the end of the bell curve? Because I said, repeat, IQ is combination of many things, right? It's at the sample average of stuff, factor add together, right? So if you believe that what you observe is something come out of a lot of random process, then underlying is a bell. That would be fine. Right? Suppose you consider business application is how much people will spend on a product is combination of many elements there, then at the end of the day, right, the thing is the bell. It's not a big deal. Okay. Of course, their scenario doesn't apply, and you have right that it may not be bell, but many of the thing is okay to assume a bell because central limit theorem tell us, right? If what you observe is averaging many factors, that is a bell. So I hope that convince you this because when you first learned it, why is a lot of assumption there, but it's not that big. Okay. And turn out that, I mean, in many applications, that is not a big deal. Of course, if you really want to make a big deal of that, it's not our elementary class can cover, right? So I hope that would convince you that is fine. Okay, so I don't want to drag you for very long because we're done with this one. Then we'll go to the other set of slide. The only thing the Excel that, I mean, probably you have to notice is this is the T. Hopefully you will use it very often, so don't worry about that when we talk about very soon in the next chapter. So maybe you can get ready for the topic 5. We will release the quiz later when we with the TA. But in the meantime, I guess we should have a break of 15 minutes, then you can do the U apply and go around to answer any question you may have. So let's resume in 15 minutes time. So we will be 14:27. Okay, that's a break of 15 minutes.
Like N-1 degree of freedom relates to how you do sample your sample standard deviation. But I was wondering if you had an explanation for that, or like because these I meant like how is it possible that students like I saw like chi-square like square or like how is it possible that or like I guess I don't know how we found out that T mimics that like is a good approximation. I'm interested in knowing this.
So this goes into protein.
Yeah. So this, so when you square that over the variation, that's chi-square. If we set that all over. With degree of N-1, that's how it's then T distribution of N-1.
Also, pi master is square that way. But this based on and also that's why what that's not that's much bigger.
So that's why degree N-1 always. And so as you do that, then you have like chi-squared like T99. This is really chi-squared of 99. Right. So that's how it connects to chi-squared the student's T. So that's basically then there's more variation. Right. Okay, that's strange. I was reading this earlier. I took a class to talk. My teacher was very interested in student like T, like he was a guy like what he said, but right, so we didn't learn. But, okay, that makes sense, so just know this.
Yes, if this is right, if that's not, I don't see any other.
Okay,
This is different.
that's fair, so just know that,
Maybe it's the department, it will be for that. It's the department, I learned what the department. They put this stuff in it. The second is. Okay, the first one. Rather.
in what, like, another class I took, like, sometimes they get mixed up, like, as, when there's a subscript of the variable, that is, like, so.
You fix it why. There's no confusion.
So you, but this would like
You
technically.
only have X, so that's why it's.
Oh,
You know,
okay,
X and Y, they are. No confusion.
okay, then,
Yeah,
yeah,
that's defined.
no, because in my other class, they made us, but so.
Yeah. You only have X and Y.
Oh, so that,
X and Y, they, specific words, sample words, and ambiguous.
yeah, okay, that,
Yeah, ambiguous.
all right, Professor, I appreciate your help, I always want to understand, how this stuff.
But this is no textbook proof, so we don't do this.
Oh, yeah, no, I understand that, especially how when I saw this, you agree my.
Nothing. The only question is how to prove this guy.
Yeah,
How to prove this guy is way beyond your recovery.
so just accept that.
Well, remember this is only proven in hundreds ago. 19 something by American general electric, or general electric, but he was not allowed to publish under his own name. He was like publish under pseudonym still. That's what it's doing.
Yeah, we didn't do a research thing on it, but we we're talking about with that T distribution, like we did a talk this last thing.
Yeah, that's really 2 weeks later. Next Wednesday.
Oh, thank you, Professor. I appreciate your help and always asking these.
Yeah, please ask because I mean, it's less, maybe let's go over then asking. We appreciate your question.
Thanks.
So let's resume. So we have 18 students have answer. So let's see what we have. Understand the T table, okay? So the T table is give you this guy, okay? It's not give you left or right. It's 1 minus alpha, right? So it's looking at the case where you give me this, I give you the number there, right? So it's not exactly the T table, rather actually the T inverse table, right? The idea because of that I give you an area here, I give you the number at the bottom, okay? So that is like the Z table, but is the inverse table, right? Because I give you it's not give you probability, right? But you give me probability, I give you what's the value of T, right? Because the Z table, what we have is like this, right? The Z table is you give me this value, I give you this area, right? So that's what the Z table tells you. But the T table is indeed is other way around, is 0 here. You give me this area, I give you this 2 number, that's symmetric. Okay. So that is slightly a little bit different because that's how we use the Z table reversely, right? So that's why the calculation is slightly a little bit more complicated. But of course, if you Excel is straightforward, right? Because T this, norm this is the same thing, right? But that is a slightly little bit complicated, okay? And look at the question again, right? To make sure that you see what's going on, right? So what we have is something like, I think negative 0.13, something like that, right? And then the question asks you to find this area, right? So what we're going to do is look at which area gives you what number and back out the area on the left-hand side. So that's what we have done. So you will do the assignment, then you will know. I mean, because without working on the assignment or the quiz, you never know understand, because in the class, we are not kindergarten class or high school or middle school class or primary. We can't go through every single thing. You actually have to do it. Okay, then you know what's not understanding, and if question, just ask the TA. And I think this is the way we do it, because if we teach every single thing in the great detail, then we can't go anywhere. But I hope that helps. But if you still have question, we're happy to go over this, go over the example again. I hope that would hopefully helpful. But the idea is like this number 1.7, right? Is like in this question, right? We know that it's like 1.7, right? So we try to look at what is the closest this area, give you this one, okay? So I hope that helps. What is central limit theorem? Central limit theorem, again, is something the following. You have the sample mean, right? You give me a distribution, whatever it looks like, right? This X, this is the sample, this is a population. And suppose you try to draw some number of here, maybe a lot, maybe 1,000 of them, okay? You draw one, then you may end up in somewhere here, right? If you draw once and you draw twice, 3 times, 4 times, you draw many of them, right? You can plot the bar chart or histogram. Then central limit tells you what it looks like. No matter what it looks like, it must be a bell. That is central limit. As long as your sample size is large enough, it will be a bell. It will be a bell curve. Okay, let me repeat the statement again. I don't care about the underlying what it looks like. Okay, and if you try to draw a sample, okay, the sample size large enough. Every time you throw a sample mean, you have many of those. At the end, it looks like a bell curve. Okay, this is central limit theorem tells you. Okay, and that is the reason why we can assume a lot of time the population, the data you drawn is for normal. That's the one reason that support that we do the T distribution or the analysis behind. I hope I answer your question. Yeah, that will we do 1 week or so. Fans, how many people we have? I think we have 60 something, almost like full house. And you ask why? Well, you can report to me whether your friend is absent, right? Or maybe we can start taking attendance if you want to. if you want. I mean, maybe we start to do you reply with the student ID taking attendance. And then those who are not coming, then will have some trouble. Okay, maybe we should do that. Do you want to do that? You want to do that? Who want to do that, raise your hand. Or who don't want to do it, raise your hand. So majority want to do that? Okay, then next time I would do I would take the attendance with that, and then that would be part of the participation to reward those who are here, since because I mean I was trying to rely on reporting, right? It seems like I have to some way to reward those who are actually here, all right? So I want to reward some of that. Monday is here. Okay. Math. Do we actually do a lot of math here? I don't think this class we do a lot of math, right? Because basically, there's some theorem we need to know, and that forms the foundation what we are doing. The speak is okay. If you question, please leave your message here. Otherwise, midterm stress. Yes, I guess the mid of the semester, or actually more than half, you must be very stressful. There are two. I think it's good that we don't have midterm, but without midterm, probably you are not doing a lot of revision. There's some troublesome that I can see here. But let's see. What do we have? Oh, I think this is not going to play the whole thing, but that is the song that we're alumni to homecoming. So probably I will come there as well because I graduated from this school, and also my friend also coming. You're welcome to have fun. There's a lot of fun goes on.
在話當年陪我踏進本部，百萬元到半空是誰在起舞？
So another one, let's see what do we have here. I don't know what it is, but I don't know what it is, but someone else doing something like this. I don't know what's going on, but so okay. So just that so one thing is important from the U reply is we start taking attendance, record your U reply next time. So the U reply will be under your student ID. So you have to log in to do the U reply. Okay. So let you see what's going on. Maybe I just do something like this. So far I didn't do it, but next time we will do an assessment. Then you will be using the login, something like that. So I will do something like this, and in the exam mode, and then you will be you have to sign, then using your CUID, where I record based on your ID there. Okay, I didn't want to do it because I want you to tell me the truth about how fast I go, but now I have to, because of attendance is a little bit easier, so I have to enforce the rule there. Okay, so now estimation. Okay, estimation. So probably why you probably ask us is why do we care what we have been doing? Okay, and later you will see the reason why we care about the distribution of the sample mean. For one reason, is because when we try to estimate things, we just don't want a single number. Instead of point estimate, which we'll define a number there, we want interval estimate. Okay, to motivate that, I guess it would be fun to look at this picture. So example like this one. No. Open. Okay, you see this particular example. Probably those who are in Hong Kong know very well, or in US will also see the same typhoon. Let's go on. Or they call hurricane in the US, right? In Asia, they call typhoon. And then you can see this particular typhoon there is a dotted line. It's a Ma'an typhoon. And then you can see the black one and the green one and the blue one. Okay. And you see the difference between the solid line and the dotted line. So actually the data, the dotted line are the prediction, and the solid line are the history. Okay. So the dotted line is actually the prediction. Our point estimate is actually the model come of the mean, a sample mean, you can say, right? How they do that is maybe them a bunch of number models, and this different model will give you different way the typhoon can go. The average of those is actually the model. It's the average of those models. Okay, and this is the best thing we can predict. That's why. Then you also see the yellow. What's the yellow? What's the yellow? Do you know what's the yellow? Yellow will be 90% of time or 80%, depending on what they're drawing, is we have confidence that most of the time is actually within the yellow region, right? So it means that when we are trying to estimate, you not estimate one point, but we estimate a bunch of points, right? In that case, if you want to shoot something, if you use a pistol, we just shoot at one point, right? If you're using a rocket launcher, then we just bomb the whole space, right? Or we want to go atomic, then nuclear, that bomb the whole area. That's the idea. It's the area of attack, right? It's not just one point, because hitting one point, we getting there is not easy. But hitting the whole area, the size of the area represent how confident our estimate is, right? The smaller the interval, right? So that would be the main goal, right? If the technology, right, then actually the range will be smaller, right? And then you also can see that the range is getting larger when you get further away, because of there more uncertainty in the future, right? So that's why in the beginning is very narrow, but at the later it's much larger. That is what the interval estimate. That's what we're going to do, right? We're trying to guess some number, right, with a sample mean, but we don't have good confidence, right? So we have to tell you instead of that number, right, there will be a good range of numbers, right? Just like in the morning, there's a financial analyst expert tell you, okay, what is today's stock price, right? It's very rare that they tell you, okay, today, believe me, today the stock price is XXXXX, a particular number. No, right? They give you a range, right? Maybe from 20,000 to 30,000. It's a big range, right? But maybe the better expert gives you a narrower range, right? Because they talk about at the end of the day what the price is, right? Just give the range instead of giving a single point, right? There's no one can able to estimate a single point there, right? So that will be the thing, right? So that's what we do, right? So that is the main idea that we're doing for this chapter, estimation, right? Using the data to guess what's going on in the big picture, right? The small picture brings to the big picture. Okay? So that's the main idea. Okay? As long as the data is representative, the thing that in the data should be represent what happened in the big picture, right? So what we want to know is called population parameter, right? Say the mean, the variance, right? Or anything you want to know, maybe kurtosis, maybe skewness, maybe range, maybe interquartile range, whatever number you can think about the data that can be estimate, right? Is usually the thing we care. And in particular, we often care is the mean, right? Of course, we also care variance. That would be something we can try to talk about, but the mean is the first thing we know, right? Because mean is the first data that representing the whole data set, right? So the mean is the thing we care, okay? And to talk about variance, another thing will be advanced class. So we just very modest talk about how to estimate mean, right? So now we come up with two terminology. It's called, have to be distinguished two things. One is called estimator, one is called estimate. Estimator is the way you do estimate. That's why it's a function, right? It's the way that you come up with estimate, right? For example, sample mean is an estimator, right? Sample mean is the way that you average observation divided by number of observation. That is the way to estimate, right? Because you use sample mean to estimate population mean, right? So that the sample mean is the estimator. Okay? It's the function. So itself is a random variable. Okay, just to remind you that estimator is a random variable. Okay, the function, right? Because every observation you have is a random variable. So estimator by itself is a random variable. But if you get a data, okay, you apply this function, okay, that become estimate, which is a number. Okay, it's a number. Okay, it's a fixed number, maybe 3 or 4 or 5, right? Depend on what you get. Okay, but there's no randomness on that one. Okay. So and very often, because the estimate depend on the sample size, this is called, that's why n is here. Okay, depend on sample size, beta n, that's what we're going to do. So as I said, estimate is a particular number there. Once we realize we collect data, okay? It depends on the sample you get, okay? So there's no randomness, but okay. Now, once we have that, where I emphasize the two things, as you can see from the satellite image, right? The dotted line is the mean, right? Which is the point estimate, right? And the way that the estimator actually gives you one number is called the point estimator, right? And what with the dot, you can see is point estimate, okay? The machine, the formula give you a number is called point estimator. The thing you actually observe in the satellite, particular realization, is called point estimate. And beside that, we have called interval estimator, right? So based on data, I give the interval, right? That is the thing. Okay, so we'll be clear very soon what we're doing, but that we will apply this for estimating the mean, right? Population mean, population variance. That's the idea. So as this example, right? In financial analysis, in the theory, they will only give you one number. Okay, that is the interval estimate. Okay, do note that it's not estimator, it's estimate. Okay, because this is number, right? If it bring, use this particular cell, then give you that one, that's the point estimator, right? But you give the number already is estimate, right? If you give the interval or blah, 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 there's interval estimate. Okay. Now we focus on very simple, the point estimator first, and we'll tell you what are the group property, okay? And now we are ready to explain in the beginning, the topic one, we say sample mean, right? It's just adding up over n. But population sample variance, you have to divide by n minus 1 or n. Okay, here we come with the explanation that is now here. So we promise, we deliver. Okay. So how to have a good estimator, right? Then there's a nice property there. Okay. Turn out we need the main property. This is the three of things we look at. The first one is called unbiasedness, okay, which will give the idea means that on average is correct. That is the normal term. On average is correct. Okay. The second one is efficiency. Okay. Efficiency means that if two things on average is correct, which is more precise, than efficiency. Okay. Less variation. That's what we said. Okay. Last one is consistency. Consistency simply means that if you expand your sample size to infinity, eventually we got what we want. Then no more uncertainty. Okay? When n is big enough, there's no uncertainty. We get exactly what we want to have. Okay? We'll give you a more definition, but that is the free property. And we'll argue that sample means satisfy all three. Okay, but let's go straightforward. So unbiasedness is on average, we hit the target. Okay, if you look at some textbook, that is what we are saying. Okay, Now, graphically, we can use shooting arrow. Okay, so suppose a guy, you're here. Okay, shooting arrow, right? And right, and the arrow is here, right? The bullseye, right? And there's somewhere here, here. All right, the many ring there, but anyway, there's an arrow here. So, and it'd be good if we hit the bullseye, right? Okay, that was the best. Every time hit the bullseye, then obviously good. But it's not always the case, right? So it's possible that you end up somewhere, sometime end up right here. You may end up right here, may end up right here, end up right here. Unbiased means that it's not there, but on average it's here, right? The average thing is in the middle, right? On average it's here, right? Need not be here, but on average here, then it's good, right? So we consider it's okay, right? So suppose, okay, there's a terrorist here, okay? There's a normal people here, normal people here, normal guy, normal guy, normal guy, normal guy, right? Suppose you have a counter-terrorist team, okay? So we try to shoot, okay? You kill this guy, kill this guy, kill this guy, kill this guy. Unbiasedness, even though we didn't kill terrorists, but we kill all the innocent people, on average we kill the terrorists. So that is what it is, okay? So ridiculous, right? You agree, right? But the problem is this very minimum requirement. If on average we didn't shoot the target, then what's the problem? Then it's problematic, right? Means because do remember, we are not going to have a machine gun to shoot many bullets. We don't shoot one bullet. We never know whether we hit it, right? Because we only do one sample. We come up with sample means we only can shoot one guy, right? But we're saying on average we're shooting the right guy. But it happened that we may shoot wrong guy every time, but on average there, right? You may never the gun actually never hit the terrorist, right? But at the end, that's what we require, okay? It's not sufficient, but it's minimum requirement. At least with hope, if we shoot enough, on average the bullet is there, but actually the bullet is not there. But anyway, that's a goal, okay? So it's unbiasedness. I hope it's clear what it means by that, right? Okay, on average, hidden target. Okay, it need not itself hit the target. It can be there's constant distance from the target. That's fine, right? It's constant error. It's okay. Okay, it's like this diagram, right? On average, hidden target is nothing is with hidden target. Okay, that's the idea. The second requirement is if A and B are both on average hidden target, okay, but it will more accurate, means the variance smaller, okay? So go back to the example that we hitting the terrorists, okay? So if we have one guy that on average hitting the red one, but we have another better elite is hitting these two guys, okay? Not further away. This guy is less variant, okay? On average, a hidden target, and the range is smaller, right? It's closer to the target, right? The variance is smaller, closer to the target, right? So that means that the blue guy is more desirable than the red guy, all right? So that means it's better, okay? More efficient. Okay, so that is the meaning of this, okay? Do note that, I mean, I'm not asking you to recall this definition, okay? It's not in the green thing, but I'm just trying to justify what we're doing here, okay? So just theory. So if you don't get it, it's okay. I mean, I hope at least you get the picture. What is in your mind there, all right? Just look at the picture. If you forget everything, it's okay. Just look at the picture, right? A and B on average in the red dot, right? Of course, they're not in red dot, but on average there, right? But A is closer than B, A is better. Okay? Now, of course, you say, okay, can we actually saying something like, we actually get to the target, right? So that's the third criteria. The third criteria said consistency, which means that when the sample is large enough, what you hit is collapse to the target. Okay? So if you look at the picture we have here is, now it must be the case, maybe the guy randomly shoot these people. Okay? But at the end we said this guy, when you give him more and more bullet, and on average we hitting the terrorists. Okay? So no matter, there's no more variation. If you give him enough stuff, we collect enough sample, okay? At the end, you're getting more accurate, there's no more uncertainty there. Okay? That's called consistency. Okay? Actually, you will see this law of large number for the mean. Okay? Law of large number guarantee this happen. Okay? So that means that if you, on average, it may be unbiased, maybe biased, whatever, okay? But on average, it's getting the right spot, okay? So consistency doesn't require on average they're correct, but just require at the end is correct. It's exactly, not even on average. So we relax in some dimension, but we were very strict on the very end, right? So I don't care about, in end it's very small, it may miss a lot, right? You may hit somewhere else. But if you have big N enough, they're hitting the right target. Okay? So that is the idea. Okay, so that, don't worry, there's some concept there, okay? Because we want to say the sample mean, right? We have been using so much time, right? So we want to say actually X bar will satisfy all the three, right? Unbiasedness, we have this set already, right? This average, the expectation of the sample means population mean, we know it. And the consistency is by law of large number, right? So what about efficiency? Okay, we didn't say it. There's a proof using some Cauchy-Schwarz inequality. They can show that the sample mean, what we use is better than any weighted mean. Okay, you can consider weighted mean or other mean actually is better than that one. But I'm not going to prove it. But you can prove anyway the combination will be not better than that one. I'm not going to prove anything. Okay. Now next, as I claim, but we don't want to do the proof because of time. You can show the following. Why we have n minus 1 instead of n? Because this is the unbiased estimate. Okay, what does that mean is the following. If I have a population, I want to estimate sigma square, say, right? I mean, I know how to estimate the mu because I collect all the sample, right? Calculate all the sample mean, and on average, it get there. But if I get a very large n, also we get there, okay? There's no problem. But we still want to estimate sigma square, right? That's something we want to know because we're not only happy with the knowing the mu, we also want to know sigma square, right? That's the second thing we want to know. How to estimate that? We argue that S square is a good one. What does that mean is, suppose I have one sample, I calculate the sample variance, right? That's S square, and another sample S square, another sample S square. With many samples, average of these S square will be the sigma square. Okay, let me draw that because that will be important. I think I want to convey the message without any single mistake. So I have a population there, right? I want to estimate mu and sigma square. And we already know that very nicely. You collect this sample, we have X bar, another X bar, another X bar, another X bar, right? Suppose we can do that. Of course, we only do one at the end, but suppose we do that, average of this will go give me the mu, exactly mu, or this one get to very large, give you the mu. No problem, without any problem. Okay. Then the next thing is, okay, how to guess this guy? The thing is, I have S square, and here I have S square, and here I have S square, and here I have S square. Okay. And the fact that if you do many of them, on average get to me to this one. Okay. And that's the reason why we have to divide it by n minus 1. If you divide by n, on average, it's wrong. Okay, so if you divide by n instead of n minus 1, we're supposed to do, that one doesn't get you the right answer. But rest for sure, no matter you use n or n minus 1, if you use super big N, they are all consistent. Okay, if you use super big N, if you divide by n or n minus 1, we'll still get you the real one. Okay, but we really want that on average is getting correct, so that's why we divide by n minus 1. Okay. Okay, so that is the reason why we do that. Okay, is that clear? So I don't want to do the proof because although the proof is very simple, only maybe 1 page of slide, but I don't want to do the proof. In case you want, there's a proof, 1 page, 2 page, 3 page of proof. It's not complicated if you really want to have fun. But this is the idea. That is the main result. You want to show this guy. Okay, and I think I explained why is you have to n minus 1 because you want, hypothetically, if you collect many samples, you have many sample variance. You want this average sample variance reveal what is exactly sigma squared, which is want to know. Okay, so that is the idea. Okay, then probably answer some of the question that what happens if you don't know sigma squared? How can you know sigma squared? Right, that's hope. If you're able to have a super large sample, which of course the sample variance give you the population variance, there's no doubt. But if you have small sample, if you do many of them, which is possible, there's hope to doing it, right? This is actually the reason behind all the political poll, right? In the US now doing right, many agents, they do a lot of interview, right, survey, and then at the end, many average of them actually give you the right answer. That's a hope, right? If on average not giving the right answer, that's a problem. So that's why unbiased is very important because many people do different things, right? If you're able to combine all the collective wisdom, we get the right thing, then it's good. Right? Is that okay? I mean, there's nothing we'll ask here, but just to explain why x bar and s squared is a good thing. Okay, I will not ask you why this is true, but I hope you still understand what's going on. I mean, I'm not particularly interested in asking the theory. All right. As I said, in this class, focus on the green thing. You understand the green exercise, example, you can do assignment, then shouldn't be an issue, right? But I hope you also understand the logic behind so that you know what's going on, right? Because right, you want to know, okay, why I am minus 1, right? That is a reason. There's a reason behind everything we do. Although we can't explain everything, but at least you know why n minus 1. Okay. So, if we are going to calculate the standard error of the mean, right, which is we learned just last class, will be sigma over root n, right? But sigma never know, right? So we will replace sigma by s. That is called the estimated standard error, right? Or estimator standard error, depends on how you write, right? So this is the way we do, okay? Now here comes to a slightly little bit complicated before we end the class is the binary data, right? And binary data, the case where the data are 0 or 1, right? Nothing new there. Everything can be applied, what we learned, but we have something new there is because of the idea that the mean and variance are related. First, that's without doubt, right? The sample proportion, which is sample mean, have all the nice property there, right? So sample mean is sample proportion is unbiased estimate of popular proportion, right? That means that if you try to ask people whether they like Trump or Kamala, right, then average that will be exactly the good estimate, right? So that is what we're doing, right? That is the idea, unbiased estimate. And because of the mean, right, and the variance are related, okay? one way to do it, to estimate the variance, is just simply use P times 1 minus P, which is the sample proportion, right? That is a good way to estimate, right? But of course, you will say, okay, this is biased because it should be n minus 1, right? Yes, you're absolutely right. But the fact that n is large in this kind of binary data, that makes no difference. So we don't bother. Okay. So of course you can say n minus 1, but there's no difference. Okay. So that's why we do that. Okay. So actually you should do that, but because n over n minus 1 is n is at least 1,000 of several hundred, at least several hundred, right? So this doesn't really matter. And the textbook, they just, okay, forget about it, just do this. And technically, if you learn further statistics, this is called method of moment. This is the way you do. You replace the this is the way you estimate. You estimate the first moment once you know how to do the second moment, but I don't want to bother you with that. But there's a solid way to why this is true, but I'm not going to explain that. Okay. But do note that it's not unbiased. Okay. But as we said, n is large enough, so that's why we make our life easier instead of correcting that, right? Because n and n minus 1 just very small difference, right? If you really want to do it, you can do that, but I would say no one actually do it in practice because this guy is so close to 1, right? Because suppose it's 400 minus 1, it's so small. No one cares. It doesn't change any result anyway. So why bother? Make our life easier, right? Because life is so complicated already, right? So make our life easy. Okay. So that's why this is our estimate, right? It's biased, but don't worry. It's consistent, everything looks very well, so it doesn't. So that is how we estimate the sample variance of the sample proportion and the estimate for that as well. Okay. So I don't want to bother you with more because I think we covered too much already, maybe a lot already. So the Wednesday, we'll come up with something very nice. It's called interval estimate. Okay. So it will be plus minus 2 standard error. Okay, that will be something we do. We'll do in the next class. End up with something more interesting thing. Actually, also the most important thing in our class is giving an estimate, right? So I think we can call today because I think many times I overrun. So I think it's good to give you 5 minutes earlier today. But in the case you have questions, just stay around until the time's over. So for those who are still confused, don't worry. I'll give the quiz. You can do online. They can text whether you know or not. Okay, I stay around to answer the question you might have if you haven't asked during the U reply.